So, now we're going to find the bounds of data. Before you start, you need to know about the two different kinds of data, and I've done a video on that so you can go back and check it. Let's just get straight into it with a problem. Now we're going to talk about discrete data first. My question is this. A cinema holds 350 people, rounded to the nearest 10. What are the upper and lower bounds of people who can fit in the cinema? What I'm saying is that they've taken the number of people in the cinema and they've rounded it to 350. So now we need to find the bounds. The lower bound, all the lower bound is the smallest this number could have been. So let's think, what is the smallest number it could have been so that they would round it up to 350 people? Well, that's easy. It would be 345. Because if you had 345 people, you would round that up to 350 people to the nearest 10. If it was 344, obviously you'd round it down to 340. So it can't be 344, and because it's discrete data, it can only take certain values, the lower bound is 345. The upper bound is the opposite. This is the largest the number could be. So what's the largest number it could have been such that they would round it down to 350? Well, again, that's pretty easy. It would be 354. Because you'd round that down to 350, right? But if you had 355, you'd round that up to 360. So therefore, we know that our bounds, our lower bound is 345, and our upper bound is 354. Have a look at the second part of this question. We need to write the limits of accuracy. This is just a fancy term for saying, what are all the values it could be, given that we rounded the number? So we know that the lower bound is 345, so we write that down. And there's a special notation here. You need to say that 345 is less than or equal to the number of people in the cinema. And the upper bound is 354, so we say that the number of people must be less than or equal to 354. So this is the limit of accuracy, and this is how we write it in this special notation. Okay, I'm going to move on to continuous data now. This is to do with time. Now, time is a continuous data because it can take any form whatsoever. Let's have a look at the question. Bob runs a race in 19 seconds to two significant figures. So we know it's already been rounded to two significant figures. We need to find the bounds and the error interval. Now, the error interval is just a fancy way of saying the limits of accuracy. So they want us to write that special notation down again. So let's have a think. What would the lower bound be? What's the lowest time Bob could run in, which we would then round up to 19 seconds? Well, the answer is simple. It's 18.5 seconds, right? Because 18.5 will round up to 19, but anything below 18.5 will round down to 80. So this 18.5 is the lowest it could be. How about the upper bound? Now, the upper bound works a bit differently with continuous data. Because continuous data can take any form, technically the upper bound would be 19.499999999999 seconds. Because if it was 19.5, technically you'd round up to 20 seconds. But because 19.4999999 is so close to 19.5, it's so close to 19.5, we write down 19.5. But we know that it will never technically get there, but it will get really, really, really close. So for easiness sake, we call it 19.5 seconds. So that is our upper bound, which means that our limits of accuracy, or our error interval, will look something like this. Now, there's a slight difference here. The lower bound's the same. The lower bound is 18.5. This will be less than or equal to Bob's time. So we'll write Bob's time. And Bob's time will be less than 19.5, but it won't be equal to 19.5. So we just do the strictly less than sign. We don't add in the equal sign. You see that? So Bob's time could be 18.5 exactly, but it couldn't be 19.5. It would be just below it. And so this is our limits of accuracy, or our error interval. Those are two simple questions. I'll do a couple more examples in another video if you haven't got to grips with it just yet.